My dear friends, we go into the next one, that is called as oxidation states. Now let us first of all understand what is oxidation state. Oxidation state is basically the charge which is being shown by the element. Charge in simple words is known as energy. So an element or any species, let it be human beings also, requires an energy when it is interacting with some other species. Remember this. When it is isolated, it doesn't require energy. So whenever we talk about an oxidation state, we are basically talking about an element which is in a combined state. When I talk about charge, it is made up of two aspects. Number one is the sign, and number two is magnitude. Now when I talk about sign, it can be either positive or negative, which depends upon the tendency to either gain or lose electron. When it is going to be losing electron, it will have a positive charge. When it is going to gain electron, it will have a negative charge. Next is, whenever magnitude is basically a number of what? Electrons, which are either gained or lost. So when I say the oxidation state of a particular element is a -4, minus means it's gaining, and how much? 4. So it's gaining 4 electrons. If I say the element is having oxidation state of +2, that means it is losing, plus means losing. How many? 2 electrons. Okay? So the charge of the oxidation state is made up of these two components, sign as well as magnitude. And I will explain to you what does the sign refer to, what does the magnitude refer to. Alright? Now, the next thing is, if you remember I told you earlier as well, and that is, the sign, the magnitude, the loss and the gain of electron always takes place in the outer motion. Alright? So now, whether the element is going to gain electron or lose electron, and that to how much, to that we need to relate it to VACC. Yes, my friend, it's VACC. So when you talk about group 16 elements, I have already explained to you, VACC of these elements is NH2 and NP4. Okay, VACC is how much? NH2 and NP4. So now if you are going to consider the octane part, okay, so that means it is deficient by 2 electrons because it has got 6 electrons. It still requires 2 electrons, so it will gain 2 electrons. So -2. This is what the general one, please remember this. Specific, it varies from one element to another. So it's -2 is the one possibility. Okay? Other possibilities, it can lose 4 electrons, so +4. Other possibilities, it can lose all the 6, so you can have +6. Okay? So these are the general ones, -2, +4, +6. लेकिन इसके अलावा भी ऑक्सीडेशन स्टेट हो सकता है, वो डिपेंड करता है कि कौन सा एलिमेंट है और कौन से एलिमेंट के साथ किस परिस्थिति में रिएक्ट है. Okay? So this is the general oxidation state. Now we go into the next one, and that is oxygen. Now oxygen generally is forming oxides. Majority of metals exist in the form of what? Oxides. And when I talk about oxides, its charge is -2. Okay? I give a simple example, say sodium oxide, potassium oxide, magnesium oxide, and so on. Next stage, it does exist in the form of peroxides. Okay, peroxide, it is -1. I give you the simplest example is hydrogen peroxide, H2O2. So uska formula, this is a molecular formula, structure the formula will be like this, HOOH. So H is +1, this is +1, so this is -1, this is -2. Okay, so oxygen is having a charge of -1. Okay, we also have superoxides. I give you a simple example, that is KO2. So that means this K has a +1 charge, so this will have a -1 charge. Okay, so this is what we have. So oxygen with -1 charge. O2 with -1. This is only single oxygen, this is double oxygen. Okay? Now apart from this, one of the most important aspects of oxygen is it does combine with fluorine and it forms fluorides. The example is OF2 and O2F. When I talk about fluorine, my dear friends, it is the highest electronegative element in the entire periodic table, and therefore it will always exist a charge of -1. So 2, 4 each, that means it's minus 2. So this will have a charge of plus 2. Similarly here, 2, 4 each is minus 2. Now there are 2 oxygen which will have a plus 2 charge. We always determine charge in terms of single species. So this will be plus 1. Okay, plus 2 divided by 2 gives you what? Plus 2. So the oxygen O2 here in this case, fluorides oxygen has a charge of plus 2. So what I want to say over here is that oxygen, whenever it combines with other elements, it shows a negative charge, except one. And that is what it is with fluorine. Okay, with fluorine, it will form fluorides, it doesn't form oxides, it will form fluorides. And having a charge of plus 2, if it is forming difluoride, or plus 1 if it is forming monofluoride. So this is, my friends, the oxidation state of the first element of this particular group, and that is oxygen. I hope you have understood this. We move to the next element, my friends, and that is from sulfur to selenium to tellurium. Polar case slightly will ignore because, as I mentioned, it's radioactive. Now, in all these elements, the most characteristic property is presence of d orbitals. In case of oxygen, the d orbitals were absent, but here the d orbitals are present. And now, with the help of an example of sulfur, you can apply it to selenium and tellurium as well. But I am giving you the example of sulfur. So, with the example of sulfur, I am going to explain you the relevance of the presence of d orbitals on oxidation state. So let us start. When I talk about sulfur, atomic number is 16 and its valence shell configuration is 3s2 and 3p4. You all know very well, my friends, that the d orbital starts from the third shell. So therefore, we will show 3s, 3p as well as 3d. And 3d like this. Now when you know about sulfur, I show first of all ground state. The lowest energy state. So 3s to 3p4, so 2 electrons over here. 4 electrons I want to arrange, so I strictly follow the Hund's rule, which says single, single, single in all the available orbitals, and then you go for pairing, so you have the pairing distance. So this is what the arrangement is. Now generally what is being said is, the number of electrons which are involved in bonding is the one which are single. Because which are there in pair, I need to supply more energy. And supplying more energy, so it's thermodynamically not possible. So here there are 2 unpaired electrons. And therefore we say the oxidation state over here comes out to be plus 2. If I talk about the hybridization also, I will show the hybridization as sp3 and the oxidation state I will show you as what? Plus 2. Okay, I am using it for ground state. If I want to make sure more number of electrons are involved in bonding, then I need to supply energy so that the paired electrons become single, so that it will be available for bonding. So that is what is an excited state. So I go for sulfur excited state. If you want to find out total how many excited states are possible for a particular element, then in simple words, the number of pairs of electrons present in the ground state is equal to the number of excited states. Once again I repeat, the number of electron pairs in the ground state is equal to the number of excited states. यहाँ पे 2 जोड़ियां हैं, इसलिए दोस्तों 2 excited state मिलेगा हमें, excited state 1 and excited state 2. तो ये हम लोग 1 consider करेंगे. Okay, so what will happen is this electron gets transferred over here. So we get 2 electrons in this case. In the 3s orbital, single, 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 and then in the d orbital, we have a single, like this. Okay, so if you consider the hybridization part, it's going to be sp3d. Now count the number of single electrons: 1, 2, 3, and 4. So that means it is plus 4. Alright, next is excited state 2. So what will happen? This is only one pair remaining, so that will get transferred over here, and as a result of which I get a single electron in s orbital, I get single electrons in each of the p orbitals, and I have single electron in each of the 2 d orbitals. Okay, like this. If you go for the hybridization state, it is like this. So it's H23D2. So you can see there are total 1, 2, 3, 4, 5, 6. So its oxidation state comes out to be what? +6. So I can give some examples over here. SCl2. So sulfur has a charge of +2. I can give an example over here as HBr4. So sulfur is having a charge of +4. Here I can give an example of SF6. So sulfur has a charge of +6. Now all these, see, +2 state, if you can see, oxygen also shows with fluorine, isn't it? फ्लोरीन के साथ वो +2 चार्ज दिखाता है, लेकिन जो होता है वो होता है +4 और +6. इफ यू कैन जस्ट चेक दिस, अगर d ऑर्बिटल नहीं होता तो दोस्तों ये चार्ज पॉसिबल नहीं था. This is what I want to explain you. The relevance, the significance of the presence of d orbitals. Okay, that is because that is responsible for the higher oxidation state, and that is +4 and +6. Oxygen does not have d orbitals. Oxygen does not have d orbitals and therefore cannot show higher positive oxidation state. Understood this? I guess this part is very clear with the example of sulfur. D orbitals are primarily responsible for the +4 and the +6 state. Oxygen doesn't have that, and therefore oxygen cannot show it. Its maximum positive oxidation state is +2, and that also when it combines with fluorine. Alright? So I hope the oxidation state is clear. Alright, my friends, we now move on to the next property, and that is about hydrogen bonding. So first of all, my dear friends, we'll understand what is hydrogen bonding is. Bonding, in simple words, is force of attraction. Force of attraction generally takes place between the two species. So here in this case, remember, is the hydrogen being bonded to an electronegative element. I can give you some examples such as nitrogen, oxygen, fluorine, and so on. It is not a bonding between hydrogen and hydrogen. Remember this. It's hydrogen and a more electronegative element. So therefore, what we can say is the strength of hydrogen bonding is directly proportional to the electronegativity of the element to which the hydrogen is bonded. Okay? Now when you talk about electronegativity of elements of group 16, the order is oxygen, sulfur, selenium, tellurium, and chromium. Okay? Next thing is the general VACC of these elements is NH2N34. So 6 electrons in the outermost shell, 2 electrons less. So that means that will be covered by forming a covalent bond with hydrogen. And therefore all these elements will form hydrides in this formula. H2O, H2S, H2AC, H2PE, and H2PO. Okay, this is what we get. Okay? Now, the next part is, when we go into the strength of the hydrogen bonding, as I said, is directly proportional to the electronegativity of the element. So oxygen is most electronegative. So therefore, when I talk about the strength of the hydrides of group 16, it will be H2O greater than H2S, H2AC, H2PE, and H2PO. So hydrogen oxide, or what we call it in simple words, water, is the strongest amongst the hydrides of group 16, and hydrogen chloride is going to be the weakest. Okay? Next is we go into the order of thermal stability. Now, thermal stability is the ability to withstand or tolerate temperature, heat. Okay? वो heat बर्दाश्त करने की जो क्षमता होती है उसे हम लोग thermal stability बोलते हैं. And that in turn is related to the strength of the bond. If the bond is more strong, it's going to tolerate more amount of heat, and therefore the thermal stability will be high. So strength of hydrogen bonding is directly proportional to thermal stability. So this is the order, my dear friends, of the strength of the hydrogen bonding. So same will be the order for thermal stability as well. So we have H2 will be having the highest thermal stability amongst the hydrides of group 16. So we have in this particular order. Okay, this is about thermal stability. We move to the next part, and that is we talk about the acid strength. Now this H plus is going to be released only when the bond is broken. So more easily the H plus is released, higher is the acidic strength. So if I want the acidic strength to be high, the release of H plus should be faster, and that means the bond should be weak. Then only it is going to break fast. And then only the H plus is going to be released faster. So the bond strength has to be released. And that is my difference in H2PO. So here the bonding is weaker. Now because the bonding is weaker, it will break faster. It will release H plus very fast, and therefore its acid strength is high. So remember my difference. Bond strength and the acid strength are inversely proportional. If the bond is stronger, the acid is weaker. And if the bond is weaker, the acid is stronger. Okay? So the order becomes reversed. So we have H2O, the least acidic, H2H, H2AC, H2PE, and then finally we go into H2P. Okay? So this is what the order that we get with respect to acid strength. When we talk about the reducing character, reducing character is also about the release of H plus. We talk about the reducing character. Is associated with the release of H plus, loss of hydrogen. Okay, that is what we talk about. So that means loss of hydrogen is oxidation, and if it is undergoing oxidation, the other substance will undergo reduction, and therefore they are going to be good reducing agents. Okay, so therefore the order of the strength of the reducing agent will also be similar to that of the strength of the acid. Alright, so this is my difference about the hydrides, or what we call it as hydrogen bonding with respect to elements of group 16. I hope you have understood this very well. My dear friends, we move on to the next phenomenon, and that is called as allotropy. Now first of all though we have to explain allotropy with respect to elements of group 16, we need to know what is allotropy all about. So, when we talk about allotropy, it is associated with same element. Okay? If the element is same, so obviously the atomic number is the same. Isn't it? If the atomic number is the same, so we say we have same number of electrons. If the same number of electrons, I say there is going to be same electronic configuration. The arrangement of the electrons will be same. If the electronic configuration is same, that means the chemical properties are same. Because electronic configuration is related to chemical properties. So, allotropy is a phenomenon where we say the element is going to be same, the atomic number is same, the number of electrons same, electronic configuration same, and therefore the chemical properties are also same. Then what is different by difference? It's obvious. There are generally two properties associated with an element, chemical as well as physical. So if the chemical properties are same, that means it's very obvious physical properties are different. Okay? So we go for different physical properties. And therefore they exist in various forms. So the different forms of the same element having the same chemical property but different physical property is known as allotropy. Once again I repeat, different forms, I'll write it down if you want, different forms of the same element. एक ही एलिमेंट का अलग अलग ग्रुप where the chemical properties are same but different physical properties. That is known as what? Allotropy. And those forms are known as allotropes. Okay, they are known as what? Allotropes. Okay, so I hope you understood what is allotropy all about. So my dear friends, with respect to allotropy, you go for the first element, and that is oxygen. Now when you talk about oxygen, it exists in two forms. The first one we call it as dioxygen, that means it's obvious it is O2, and the next one we talk about is ozone, which is O3. Okay, now when you talk about dioxygen, O2, it's going to be existing in the form of a colorless gas. Whereas here, when we talk about ozone, it can exist in three physical states. And that is, when it's going to be in a gaseous state, it's going to be blue. When it's going to be in a liquid state, it is violet blue. When it's going to be in a solid state, it's going to be black. So you can see the intensity of the color increases as we go from gas to liquid to solid. Of course, here we can say that it can be liquefied and it will give you a pale blue liquid. Okay, that's what I said. The structure when you talk about of this oxygen is double bond. But here it is having an angular structure, that is this. Okay, there is a double bond on one side. The one angle is going to be around 170 degrees. This is what ozone is. Okay, you can shift this double bond on this side. So we have another resonating structure like this. Okay, so it is having an angular structure. This is linear. We call this as angular. Next one is, according to molecular orbital theory, oxygen molecule, the dioxygen O2 has two unpaired electrons. And because of the presence of two unpaired electrons, we say it is going to be paramagnetic. Whereas here, all electrons are paired. And when all the electrons are paired, so we say that it is going to be what? Diamagnetic. So you can see over here, the basic differences which I have outlined is in terms of color, is in terms of structure, is in terms of the magnetic properties. And my dear friends, you all know this very well. All these properties are physical properties. And if you can recollect, what did I say in allotropy is, the element is going to be the same, the chemical property is also almost going to be the same, but then the physical properties are going to be what? Different. And therefore, the dioxygen and ozone are going to be considered as allotropes of oxygen. So I hope you have understood this concept. Now, my dear friends, we go into the next element, that is about sulfur. So, when you talk about allotropy with respect to sulfur, there are various forms of it. We will only consider the major ones. The first prominent form of sulfur that we have is called as rhombic sulfur. Okay, it is also being called as alpha sulfur. Powdered sulfur is going to be heated in a solution of carbon disulfide. That results in the formation of rhombic sulfur. Its specific gravity, that means density in comparison to water, is 2.06. The arrangement of this is crown shape, which we also call as a pucker ring structure, and that is going to be in this fashion. So if you can count 1, 2, 3, 4, 5, 6, 7, 8. So we call it as SA ring, a crown shaped ring. Or we also call it as pucker ring structure. So this is about rhombic sulfur. Now, next one we have is monoclinic sulfur, which we also call it as beta sulfur. Heating of rhombic sulfur results in the formation of beta sulfur. So you can see now that there is a possibility of conversion of one form into another form simply by changing the temperature. And this is physical means, and that's why we say allotropes have difference in their physical properties. Now, as far as the temperature is concerned, I would like to say that this is going to be stable about 368 Kelvin. And that means this will be considered as a transition temperature. So, if I were to keep it say 368 Kelvin like this, and if I go on the right hand side, that means above 368, then we say beta sulfur exists. And if I go below 368, I will say alpha sulfur exists. Okay, so this is called as a transition temperature, where at 368, alpha as well as beta coexist. Now, when you talk about monoclinic sulfur, what happens is that by heating of rhombic sulfur we can get this, and also followed by cooling. Okay, because we need to cool it. and that results in the formation of needle-shaped crystals. Okay, when I talk about needles, so you understand this very well, it's only very fine, it's very thin. The third important form of sulfur that we talk about is called as plastic sulfur. We also call this as a gamma sulfur, where sulfur is going to be heated and then it is being cooled, which results in the formation of a rubber-like soft solid. Okay, it is in the form of rubber-like soft solid. Now, as far as this arrangement is concerned, it's like a zigzag structure in this way, open chain structure, where sulfur atoms are being connected with each other. So this is zigzag, we can say. Now there is also changes in terms of specific gravity is concerned. As I said, the specific gravity of alpha is 2.06. So here it is somewhere around 1.96 and this is around 1.95. This is the specific gravity of the three forms. The final form, the most important one, and that is we have, and that is called as colloidal sulfur. Now when I talk about colloidal sulfur, it's related to colloids. It's a system where the particle size matters. My dear friends, when a solute is completely soluble in the solid, the particle size is minimal. We call it as a pure solution. When a solute is completely insoluble in a solid, we call it as a precipitation taking place, where the particle size is maximum. And in between these two, we call it as a colloidal system. So colloidal particles are those whose size is going to be greater than the true solution, but less than that of the precipitator. That is what colloid is. Now the easiest way of preparing a colloidal sulfur is by a chemical reaction, and that is a treatment of nitric acid with H2S. So that results in the formation of colloidal sulfur plus NO2 as well as H2O. Okay, so this is the colloidal sulfur that we get. Here a piece of caution which I want to say, and that is, don't drop a downward arrow here. Okay, because the downward arrow indicates precipitate and we are talking about what? Colloid. So these are the major forms. Apart from this also there are other forms of sulfur, but then we will be considering these four forms: the alpha, the beta, the gamma and the colloidal sulfur. So I hope you have understood this. Alright, so now we go to the next element, that is selenium. The predominant three forms, there are many forms also, but the predominant three forms of selenium is, the first one is the red form, second one is the grey form, and the third one is the black form. These are the three predominant forms. Other forms are also there, but these are the most dominating ones. And you can see it is based on color, and color is physical property, my dear friends. Okay, next is we go into tellurium. Tellurium has got two forms. First one we call it as a metallic form, and the other one is non-metallic. And as I told you earlier also, that tellurium is a metalloid, and therefore it can behave as a metal as well as a non-metal, and therefore we can show these two forms. And finally we go for the last element of this group, and that is polonium. Polonium exists in two forms. There are two arrangements of particles. First we call it as the alpha form, and the other is called as the beta form. Polonium is radioactive, but one more important thing which I will say is it's distinctly a metal. And therefore it is very obvious that alpha and beta, both of them are the metallic forms of polonium. Alright? So this is, my dear friends, all about the allotropy with respect to elements of group 16. We started with oxygen, if you remember. So we have oxygen, we have got dioxygen as well as ozone. Then we have got sulfur, the four important forms which I discussed with you all. Then comes selenium, tellurium and polonium. So I hope you have understood this concept very well. Thank you.